All right, today we are diving into some really cool new research that shows how scientists are literally forging a new material to take on CO2 emissions. It's all about turning a huge global problem into a potential solution. And get this, it's all powered by sunlight.
I know, it sounds like something straight out of science fiction, doesn't it? But that exact question is driving some of the most fascinating science out there right now. The big idea is to create a kind of artificial photosynthesis. But to pull that off, you need a really special type of material. And that material is called a photocatalyst. You can think of it as a tiny, microscopic solar panel and a chemical factory all rolled into one. It basically soaks up sunlight and then uses that energy to kickstart a chemical reaction, in this case, turning CO2 into something else. It's a fantastic idea, but there's been this one major problem that's held the whole thing back for years.
Okay, so let's get right into it. To really get why this new discovery is such a big deal, we first have to understand the hurdle they were trying to overcome. Why has it been so incredibly difficult to make a good photocatalyst for converting CO2?
Well, the main issue is basically an energy leak. See, when sunlight hits the catalyst, it creates these little energized particles. But the problem is, in most materials, those particles just snap right back together almost instantly. It's like a battery that immediately short circuits. All that captured sun energy just turns into useless heat before it has a chance to do any real work on the CO2. So, to fix this short circuit problem, scientists figured, hey, what if we combine two different materials? The idea was to build a dream team where each material brings its own special skill to the table to capture and use that light energy way more efficiently. Now, I know this slide looks super complicated, it's pulled right from the research paper, but the main idea is actually pretty simple. Scientists are mixing two key ingredients here. On one side, you have carbon nitride, that's the part that does the actual chemical reaction, and on the other, you have these tiny things called carbon quantum dots, which are amazing at absorbing light. The whole goal is to get these two to work together perfectly.
So here's the breakdown. The carbon nitride is our workhorse. It's where the reaction happens. The carbon quantum dots, or CQDs, they're the energy boosters, capturing sunlight and helping to shuttle that energy where it needs to go. I mean, on paper, it sounds like a perfect partnership. But there was one big nagging flaw in how they were connected.
The problem was, in all the previous attempts to combine them, the two materials were just kind of stuck together by these really weak forces. Think of it like Velcro. The connection just wasn't strong enough, so you couldn't get a smooth, fast transfer of energy between them. It was slow, it was inefficient, and you guessed it, we were right back to that short circuit problem. So the big question became, how do you upgrade that connection from flimsy Velcro to something permanent? Well, this is the breakthrough. They found a way to force the two materials to forge a true unbreakable chemical bond, something we can think of as a covalent handshake. And the process they came up with is just so direct and clever. First, they just mix the two materials together in water. Then, and this is the key part, they blast that mixture with a high-energy electron beam. This beam acts like a microscopic welding torch. It zaps the materials, breaks a few of their old bonds, and forces them to fuse together, creating new, super strong covalent bonds. Okay, another really busy slide from the lab, but you just need to focus on one thing. See the image in the top right, the one labeled E? Those tiny grid-like patterns, those are the quantum dots. And you can see they are literally embedded, fused, right onto the larger material. This is the microscopic proof. It's not just a mixture anymore. It's a single, brand new, unified material.
So yeah, they basically threw out the Velcro and brought in the superglue. This new, powerful bond creates an energy superhighway. It allows energy to flow instantly from the quantum dots to the workhorse material. And the energy leak we talked about before, it's been sealed shut. Of course, the real question is, does all this actually work in practice? I mean, a stronger bond is great in theory, but did it really make the catalyst better at converting CO2? Well, let's take a look at the results.
And wow, this chart just says it all. On the far left, that tiny bar is the original carbon nitride all by itself, not doing much. The middle bar, that's the Velcro version, where they're just mixed together. A pretty big improvement for sure. But then look at the bar on the right. That's our new superglue material forged with the electron beam. The performance isn't just better, it's in a whole other league.
Let's just zero in on that winning number for a second. 44.5. That number represents how fast the new catalyst can turn CO2 into carbon monoxide, or CO. And CO is really useful. It's what's known as a chemical feedstock, a basic building block you can use to make sustainable fuels and all sorts of other chemicals. This is a massive jump in efficiency. And just to put that in perspective for you, this new superglued catalyst is almost 7 times more effective than the original workhorse material was all on its own. It's just incredible proof of how vital that strong, permanent bond really is.
And check this out, it's not just a one-hit wonder. Don't worry about all the data points here, just look at the graph in the top left, the one labeled C. It shows how well the catalyst performed over a full 24 hours. See how that line stays high and flat cycle after cycle? That superglue bond isn't just strong, it is incredibly durable. This thing is built to last.
So let's step back and look at the big picture. Why is this specific discovery so important? Well, it's about a lot more than just this one new material. So let's just quickly recap the big wins here. That stronger bond creates the energy superhighway, which means way better performance. The process also happens to make the material's surface better at grabbing CO2 out of the air. It all adds up to much higher efficiency and, as we saw, fantastic stability over time. But this right here is the real takeaway. Honestly, the most exciting part of this whole story isn't just this one amazing catalyst. It's the method they used to create it. This electron beam technique is a powerful new tool in the toolbox, a whole new way to think about building super high-performance materials by literally forging them together at the nanoscale. And that really leaves us with a huge, exciting question for the future. If this method can revolutionize a catalyst for CO2 conversion, what else could it do? Imagine using it to create materials that can cleanly split water to make hydrogen fuel, or new catalysts that can purify our air. The possibilities are just immense when we learn how to build a better world, one microscopic bond at a time.